Hi everyone. My name is Jean-Marc, and I'm going to talk. I work for Salesforce, and I'm going to talk to you today about how we built a metadata store using Akka-http. So here's my agenda. I'm going to first introduce Akka and the actor model, and I will talk a little bit about what we do at Salesforce, especially in the field of machine learning and data science. And then I'll go a little deeper into a case study of how we built a data store service to store our metadata. And then I'll share our experience and our learnings from using Akka-http and Akka. So this is probably not the first introduction to Akka you've had this week, but forgive me, I'll do another one. Akka is a JVM implementation of the actor model. It's built with Scala and provides a Java API. And the actor model basically is a mathematical model for doing concurrent work. And basically, the system is broken down into actors that are entities that do the work, and actors talk to each other via messages. They have a state and a behavior, and they can only change each other's state by sending messages to each other. Actor systems have a hierarchy, a parent-child type of hierarchy, and a parent actor manages his children. So now I'm going to talk about the specific implementation of the actor model using Akka. Akka provides an actor system class that you instantiate, and it will manage your actor lifecycle and the communication between actors. And it will also manage its own thread pool, and it will allocate threads as needed when the actors actually have a message to process. And then you have all the actors. Each actor is roughly 300 bytes. They are pretty lightweight. That means you can run on 1 gigabyte of memory, you can run over 3 million actors. So it's much more efficient than using threads it's much more, you can fit much more actors in your memory than if you had to use threads. Actors in Akka have a mailbox, a supervisor, which is the parent, and possibly child actors. And so all messaging is asynchronous, so actor A can send a message to actor B, and sometime later in the future, actor B can respond and send a message to actor A. Akka comes with extensions. There is the Akka remoting extension for actor system to talk to a remote actor system. There is the Akka cluster extension for spreading your actor system over multiple machines, and Akka stream for doing stream processing using actors. Akka persistence for doing actor backup, actor state persistence and recovery. And so, of course, there's a lot more extensions. This is just not an exhaustive list, and you can also write your own pretty easily. And then the extension we're going to look at today is Akka-http. Akka-http is the toolkit that lets Akka actors use HTTP to communicate with the outside world. HTTP is the most common protocol to exchange data today. And so Akka-http comes with a client and server API. It uses Akka streams to handle HTTP connections using actors. And it has a very expressive, functional, and intuitive DSL that actually originated from the Spray.io project. The people that were working on the Spray.io project are now working fully on the Akka-http project. It's great for APIs and RPC in a microservice environment. It's not so great for rendering things like templated HTML. A quick summary to recap about Akka. Akka is very good for high concurrency. It lets you maximize the use of your computing power. It's good for fault tolerance and resilience. You can basically decide what you want to do if a child actor fails. You can restart it, or you can spin up a new one. It's easy to extend with the extensions that I just mentioned, and easy to scale out using Akka cluster. It's used by, or been used by popular projects. It was used in Spark up to version 1.4, and then they switched to their own custom RPC layer. It's used by Flink for doing stream processing. Flink actually uses the Java API. It's a fun fact. And used by Play and Spray. Now I'm going to talk to you a little bit about what we do at Salesforce. Salesforce is a cloud CRM company. CRM stands for Customer Relationship Management. And we basically help our customers manage the relationship with their customers. Our CEO, Mark Benioff, is a very big advocate of using data science and machine learning to make the CRM more intelligent. And he's been very clear that this is the direction we're going in the future. And so in the past couple of years, we've acquired a few companies, such as MetaMind, Salesforce IQ, and Prediction.io. MetaMind does NLP and image classification using neural networks. Salesforce IQ does a smart CRM, and Prediction.io is an open source machine learning platform that actually uses the Spray.io project. And so recently at Dreamforce, we announced this initiative that pretty much drives the whole effort towards more data science and more machine learning into the product. And that initiative has been labeled Salesforce Einstein. So what is Salesforce Einstein? Salesforce Einstein is AI for everyone. It's for our customers who are using our product. It's for data scientists when they want to create new intelligent features in their products. And it's for external developers. Salesforce is pretty big on the developer community. We have something called force.com, which allows any developer to sign up and come and develop their own applications on top of the Salesforce platform. And so we're going to continue in that trajectory. The goals for our engineers for the platform is that we don't want our customers to do ETL, so we have to handle that for them. A big pain today of doing machine learning and data science is you have to prepare the data, ETL, and clean it. We want to take that effort and make it easier for our users to use the platform. We don't want necessarily to restrict the platform to people with advanced degrees in machine learning and statistics. So we say no PhD required. And we want the platform to be scalable because we have a lot of customers, a lot of data, and we want it to be reliable. So now I'm going to dive a little deeper into what our platform looks like in the technical side. We are basically performing three functions. We're doing ETL, so we transfer data from Salesforce, the Salesforce API, into our environment, and we convert it to from CSV to Avro, and we prepare it for machine learning. In the future, we'll also be ETLing from other sources. We're doing scoring on the data and pushback. We're pushing the score back to the Salesforce core platform. We're also periodically retraining models because we want the models to be accurate. And so these are the three tasks that we're focused on. We have a strong partnership with AWS and a lot of experience with using things like Amazon EMR and S3. And so we're going to leverage that, and the whole platform is going to be on AWS. And so we heard about this cool technology called microservices, and we're definitely going towards that. So you can see on the right side a basic diagram of some of our microservices, and then they're executing jobs against Amazon EMR. So we want to pick for our platform, we wanted to pick the right tools for the job. So our engineers have a lot of experience with Scala and Spark. And so we're using that for data processing, running Spark jobs on EMR, writing the data to S3. S3 is great because it allows us to not have to have a Hadoop cluster permanently up, and we can save on operation costs. One of the critical pieces of the architecture is our executors microservice. Its function is to monitor Spark jobs from Amazon EMR, and it's also running our ETLs from the Salesforce API. And that piece had to be very resilient, scalable, and fault tolerant. So we decided to use Akka actors and Akka cluster to implement that microservice. And so for the rest of our Scala microservices, we decided to use Akka-http to connect them together. We've had some of our engineers had a lot of experience with Spray.io, and they were very adamant about the DSL. And so we decided to leverage that for the communication between our microservices. So now, going back, I'm going to go into more detail about this microservice called Datastore. I'll state the problem that we were trying to solve. So when we ETL data from Salesforce, we know a lot of things about the data. We know where it comes from, which API, which customer, what time we pulled it, what it is, how many records, what format, and what schema it's in. And this information can be very useful for machine learning and in subsequent operations down the pipeline. And so we wanted to be able to keep track of that metadata. And so what we've been doing in the past, before, in previous years, we used in S3 the path to store all this information. Not all this information, but some information. So for example, we would store in a path that would look like this. We would store the information that the data is in CSV format, and it belongs to this company, and then it was saved on this date. And we will use that to be able to identify what this file is when we want to use it. So that presents a couple issues because first of all, there's a limited amount of information you can store in the path, and also it requires you to query the information in the order of the path segments. So it forces you to use a certain sequence of predicates when you want to find information. So we decided this was not a good solution. So we built a microservice called the Datastore service using Akka-http. And we connected it to a Postgres database. And basically what this Datastore service allows us to do is whenever we want to save a file to S3, we are also writing a record in the Postgres database, sending a record to that data store that contains all the information about this file. And so by keeping these two things in synchronization, we're able to do a nice abstraction over the S3 file system, and we're able to answer very complex queries about the data. So for example, we can say, can you give me all the unprocessed CSV files for this customer? Or can this file of scores, or can this model score this file that has schema Z? And it also allows us to do very advanced features, such as data lineage. So if we have a file with scores, and we want to know the history of this file, we can trace back that it was generated from this Avro file. This Avro file was converted from this CSV file, and this CSV file was pulled from this ETL job. So it's very useful for troubleshooting and debugging all this data. This is an example of what metadata we store about each file. So we have an ID and the company, the format, the schema ID, because some files can share schema. And we have even more metadata. And here we have the location of all the files. It could be one file or more files in S3. And the good thing is we're not necessarily stuck to S3. If we ever switch to something like Alluxio or Hadoop, then we can also switch to that. So now a little bit more details relevant to Akka-http. I wanted to show you, give you an idea of how nice the DSL is for writing HTTP routes. So here's an example of two routes, a post route and a get route. And you can see that I'm basically creating a route value, and I'm binding it to this IP address and this port. And let's analyze the route. So each of these keywords, each of these function calls are called directives, and they basically allow you to filter HTTP requests coming in and that's how you implement the route. So path, post, and get are directives that filter the route. Akka-http comes with a lot of, pretty much everything you can find in HTTP, such as put, patch. Those are predefined routes, directives, sorry. And so when you want to chain routes together, you use the tilde operator. And if the first route is rejected, then only then the second route will be evaluated. The complete function call actually closes the route and returns the HTTP response to the server. This HTTP function call is the Akka-http extension, and that's how you instantiate it. So again, very simple, very easy, very functional in the structure. And when you have this in your code, you can basically, this becomes a value, and then you can also concatenate two values together, and then you have a very nice way to represent your route. Directives can match on any HTTP attribute. You can also write your own directives that basically look at the HTTP request for things like headers, and that's how you can do things like authentication. Now I'll share what we learned while using Akka and Akka-http. So using Akka and the actor model for ETL was very, very nice because all our actors are lightweight, and they're very good for infrequent activities such as polling for the status of Spark job. So what they do is they wake up and they query the EMR server, and then if the Spark job is not completed, then they go back to sleep, and we don't use any thread. We don't have any thread utilization at all. Akka-http has a very nice DSL. We're very impressed. And has all the HTTP constructs that are in the RFC. And you can also do very complex, more complex things than routing. You can do request proxying and routing. And you can do things like WebSockets. And like I said, routes are very easy to maintain and troubleshoot, especially if you have an IDE that lets you click through to the value definition. Bit of warning, actors are maybe lightweight, but they do need an actor system. So Akka-http might not be suited for simple clients. So if you have a simple lightweight, you want to make your client lightweight and only want something that can talk HTTP, it might not be the best solution because you need to spin up an actor system if you want to use Akka-http. The actor model has a learning curve. You have to think about how your application can be modeled using actors, and that's not necessarily, it's something you have to learn a little bit more about the actor model to be able to do. Akka-http comes bare bones by design. It's very clear in the docs that it's not a web framework. So things like CORS and CSRF need to be implemented, or you can use third-party libraries. So to finish, I want to give you, based on our experience, these are the libraries that we used. We use CLC. It's very, very good for doing JSON serialization, encoding, decoding. TypeSafe config is a very nice library for environment and configuration. It's actually the one It's from Lightband, and it's the one that Akka is using by default. We used Slick for doing ORM on top of our database. Hikari-CP for connection pooling, Flyway for database migration, Akka-http session for things like authentication and JWT tokens, and Akka-http test kit for testing our routes. And that's it for my presentation. Thank you very much. If anybody has questions. Question?
Yeah. You mentioned that vector system is not suitable for lightweight services. What exactly do you mean by that? It's kind of advertised as very light.
So the actor system itself spins up. It spins up. I mean, it is also lightweight, but it spins up a lot of things you might not necessarily want when you just want to do a HTTP client. And it also has, if you don't configure it properly, it can also have a lot of things you might not want. But it's still not a... Yeah.
Okay, why don't you pick your JSON serialization library? According to what reasons?
So we tried it and we liked it. But there are other libraries. There's the Akka spray JSON library. But the good thing with Cersei is you can use implicit encoders in your code, and so we really like that. But yeah, sorry, I don't have a better answer. Yep. All right. Thank you.